Assalamu alaikum. Today we are going to discuss the vibrational energy level of a polyatomic molecule. So the vibrational energy levels of a polyatomic molecule depends on the vibrational mood, or we also call them vibrational degrees of freedom. The number of vibrational degrees of freedom depends upon the geometry of the molecule, whether it's a linear molecule or a non-linear molecule. So if we have an individual atom, so there are 3 degrees of freedom associated with translational motion along 3 different directions. So if there are n atoms in a molecule, so a molecule will have 3n degrees of freedom because there is 3 degrees of freedom associated with one atom. So in one molecule, if there are n atoms, so the total degrees of freedom for a molecule will be equal to 3n. Out of these 3n degrees of freedom, there are 3 degrees of freedom associated with the translational motion of the molecule. And if it is a linear molecule, so there are 2 degrees of freedom associated with the rotational motion of the molecule. For example, this one is a linear molecule and that is oriented along z-axis. So it can only have rotation about the x-axis and rotation about the y-axis. Its rotation about the z-axis is meaningless. Similarly, if we have a non-linear molecule, so the number of its rotational degrees of freedom are 3 because it can rotate about z-axis, it can rotate about x-axis, and it can rotate about y-axis. So the number of vibrational degrees of freedom for a linear molecule must be equal to 3n, which is the total degrees of freedom for a molecule, minus 3, which is the 3 translational degrees of freedom, minus 2, which are the 2 rotational degrees of freedom. So if you minus this translational and rotational degrees of freedom from the total number of degrees of freedom, so it will give you the vibrational degrees of freedom. So for a linear molecule, the total number of rotational degrees of freedom or the number of vibrational mode is equal to 3n minus 5. Similarly, the rotational degrees of freedom for non-linear molecule will be equal to 3n, the total number of degrees of freedom for the molecule, minus 3, the 3 translational degrees of freedom, minus 3, the 3 rotational degrees of freedom, and it comes out to be 3n minus. Sometimes these vibrational degrees of freedom are also known as the internal degrees of freedom because this vibration is associated with the internal motion of the individual atoms of the molecule. So we have 3n minus 5 degrees of freedom or vibrational mode for linear molecule and 3n minus 6 vibrational mode for non-linear molecule. So the vibrational modes has two types, stretching and bending. While the stretching is associated with the change in the bond length, while bending is associated with the change in the bond length. The stretching is further divided into symmetric and asymmetric stretching. For example, this one is symmetric stretching. So you see that these two outer atoms go out and come in simultaneously. So this is the example of symmetric stretching. However, here the situation is different. One molecule go in, so the other molecule go out. So this is an anti-symmetric stretching. While here we have the vibration in such a mode that there is a change in the bond angle, and this is known as the bending. So if we have a linear molecule, so if we have carbon dioxide, so here we have two atoms, for example, one carbon and one oxygen. So the number of vibrational mode will be equal to 3 and to 2, where n is equal to 2 minus 5 is equal to 1. So there is only one vibrational mode, meaning there is one mode of vibration. So here we see that a diatomic molecule can only vibrate along this one particular axis, and there is no other direction of vibration. Now, if we take the example of polyatomic linear molecule. Let's suppose carbon dioxide. So here we have N is equal to 3. So why 3? We have 1 carbon and 2 oxygens. So the total number of atoms is equal to 3. So according to the formula, there will be 4 vibrational modes for the carbon dioxide molecule. And these 4 carbon vibrational modes for carbon dioxide are the symmetric stretching, the anti-symmetric stretching, and the bending. So here we have 2 types of the bending. One is this up and down, and this one is back and forth. If we have a non-linear molecule like that of water, so there are again N is equal to 3, 2 hydrogen and 1 oxygen. So according to the formula for the non-linear molecule, there will be 3 vibrational modes. And those 3 vibrational modes are the one is the symmetric stretching, the second one is the asymmetric stretching, and the third one is the symmetric bending. Now, if we look into the different vibrational modes of water, so there are different energies associated with different vibrational modes. For example, this one is the symmetric stretching. So for the symmetric stretching, we have this much energy. For the asymmetric stretching, the energy is being increased, and then the asymmetric stretching, so the energy is further increased. So we don't have a particular single energy level for one molecule, but there are different energy levels associated with different modes of vibration in a single molecule. So we have to take care of these different vibrational mode. In some cases, the vibrational mode are independent from each other, while in some cases they mix together and they give us superimposed vibrations, so the spectrum become more and more complicated. Here again we have the example of carbon dioxide. So there are different vibrational modes. For example, for the symmetric bending, so there are 2 types of symmetric bending. One is this up and down, and this one is this back and forth. So there is the same energy for this bending. And now here we have for the symmetric stretching, so the energy has been increased, and for the asymmetric stretching, we have still we have again higher energy. So the carbon dioxide molecule has 4 different vibrational modes, but these 2 vibrational modes, they have the same energy. That is why in a carbon dioxide molecule you will have 3 energy level instead of 4 energy level, because the 2 energy level symmetric bending, they are exactly the same. So they superimpose over each other and they give a single energy level. So if we look into the FTIR spectroscopy, so here we have water molecule and carbon dioxide molecule, and the water molecule has the vibrational energy at different energy state. The carbon dioxide has vibrational energy different energy state, and so on. Now you see that we don't have a single vibrational mode for water and carbon dioxide, but we have multiple mode of vibration for the water and carbon dioxide, because hydrogen, water and carbon dioxide have multiple vibrational modes. Also, some of the molecules that consist of functional groups, and each functional group has a particular frequency, and with those particular set of frequencies, we can identify the molecular structure. For example, some of the well-known functional groups are OH group, and it has a frequency of 1.1 10 to the power 14 Hz. The NH2 group, it could have a frequency of 1.0 10 to the power 14 Hz. So whenever we see frequency lines of these values in a particular infrared spectrum, so we can say that in this particular molecule there are OH and NH2 groups are attached. Similarly, we have 3 different frequency for carbon bonding. When there is a carbon-carbon single bond, so we have this much frequency. When there is carbon-carbon double bond, so we have this much frequency. And when there is a carbon-carbon triple bond, so we have this much frequency. And we see that as the number of bond increases, so the frequency also increases. And this is because of the increase in the force constant value. When the bond is stronger, so you can say that the bond is stiffer, and if the bond is stiffer, so the value of K is higher, and if the value of K is higher, so the frequency is higher. So in this case, we see that is the number of bond go on increasing, so the carbon are more tightly bound to each other, and the elasticity go on decreasing. So that is why we have more and more frequency. As we said earlier, that the functional groups are helping in identifying the molecular structure of a molecule. So for example, we have a thioacetic acid. It could have a molecular formula of this one or this one. But if we study its infrared spectrum, so we see that there are only lines for CO group and SH group, and there are no line for CS or OH group. It means that this is an incorrect formula, while the correct one is this one. So if I summarize this presentation, so we see that vibrational energy level depends on the mode of vibration. Each mode of vibration within the same molecule has different energy of vibration, and the number of modes of vibration depend on the geometry of the molecule. That is, if it is a linear molecule, so the number of vibrational modes are 3 and minus 5. If it is a non-linear molecule, so the number of vibrational modes are 3 and minus 6. And a vibration could result in stretching or bending of the bond, and there are some functional groups within a particular molecule which has specific vibrational energies, and the strong bonding correspond to the higher vibrational frequencies, and we can identify the particular functional group from those frequencies. So I hope you may have understood it, and this was all about the vibrational energy levels of the molecule. So the next talk will be about the vibrational rotational spectra, and then the last one will be about the electronic spectra. Okay, thank you. Allah Hafiz.